We have two more things to learn about truth tables, namely how to use them to test sentences for equivalence and how to use them to test arguments for validity. Let's start with equivalence. The idea here is that when two statements have the same truth value, when two statements have the same truth table, they are equivalent to one another. We call this truth functional equivalence when we're being really strict. But the basic idea is that two sentences are the same when they have the same truth table. That makes sense, right? So I've set up two truth tables here. Let's do this first one on the left. We'll look at this truth table. And what we want to show is that under the main operator of each of these two sentences, we're going to get the same pattern of T's and F's. Okay? In other words, on each truth assignment to the atomic propositions A and B, we'll get the same truth value for each sentence on every line. Okay? Now, this is just a disjunction, so we know it's true whenever at least one of the disjuncts is true, and it's false when both disjuncts are false. If that was too quick for you, if you didn't understand that, you need to go study the master truth table and then come back and listen to the rest of this video. Now, the order of the propositions is different in this case, right? This is a disjunction A or B. The second sentence is also a disjunction, contains the same atomic sentences, B and A. They're just in a different order. And you would expect that A or B means the same thing as B or A. But here's a proof of it. We have true, 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 and false. And once again, the only time that this disjunction is false is when both disjuncts are false. That's on the fourth line. So what we find under these two main connectives is the same pattern, T, 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 F in both cases. And that means that these sentences are equivalent. Now, just to be perfectly clear about what we mean here, let's do another case over here where we've got an inequivalent pair of sentences. These are both conditionals, but they go in opposite directions. The first one has A as the antecedent, C as the consequent. The second one has C as the antecedent, A as the consequent. And we'll see that this makes all the difference. Now, I did tell you that you only need to fill in enough of a truth table to prove what you're trying to prove. In the case of equivalence, you actually have to give a truth value for every sentence on every row of the table, because if you don't have them all, then you might have missed one where they're different. But in the case of proving invalidity, you only need one case where they're different. All right, and that's going to turn out to be here on the second truth assignment. Now that's the truth assignment that makes the first conditional false, because then we'll have a true antecedent and a false consequent. And that TF case is the only case that makes a conditional false. Well, if we switch the order of the antecedent and the consequent, now C is the antecedent, C is false, A is true. In the master truth table, that's the third line, false antecedent, true consequent, and that makes that sentence true. So in this case, we have false for the first sentence, true for the second sentence, on this same truth assignment. So think now about this definition up here. It says that two sentences of the SL are equivalent to one another when, on each truth assignment, the sentences have the same truth value. Well, this second truth table shows the opposite kind of situation. This is a case where these sentences are not equivalent because there is at least one truth assignment where the two sentences have a different truth value from each other. Okay. Now, with truth tables never speak for themselves, so you have to always give an explanation. Here's the kind of explanation that I'm looking for. It doesn't have to be word for word, but it has to capture the right ideas. On the left, it says this truth table shows that the sentences A or B and B or A are equivalent because on each truth assignment to A and B, their atomic propositions, the two sentences agree in truth value. Okay, that means that they're the same on each truth assignment. That's the kind of explanation you need for equivalence. For non-equivalence or inequivalence, say something like this. There's at least one truth assignment, in this case where A is true and C is false, where the two sentences have different truth values. That means they're not equivalent. All right, so far so good. Let's look at some other examples. Here's a couple of sentences, not A or B. That's a negated conjunction. and we're comparing it to a disjunction where both of the disjuncts are negated. And what we'll find is that the main connective here is this one, and the main connective here is this one. So it's the truth value under the negation in the case of the left sentence and under the wedge in the case of the right sentence, which are the truth values that will matter to judging equivalence. Now, how do you do quickly a truth table for a negated conjunction? Well, I start just by doing the truth table for the conjunction, and then I just negate that. Oops, sorry, missed that. Now, how do you do the truth table for a negated conjunction quickly? I start just by doing the truth table for the conjunction, just looking at the parentheses first, and then negating that, right? So the T becomes an F, this F becomes a T, this F becomes a T, and the last F becomes a T. So that's the main connective, so we can circle that like that. Okay, good. So that's the first truth table completed. Now for the second sentence, we have a disjunction. Disjunctions are true when at least one disjunct is true. On the first line, since A is true, that means that not A is false. And when B is true, not B is false. So we have false, false in a disjunction here. That means the disjunction is false. On every other line, we're going to have at least one true disjunct. That's because when B is false, not B is true. And that means in that case, since not B is true, we have at least one true disjunct. That's enough to make the disjunction true. On line 3, where A is false, that means that not A is true, and that true disjunct then means that the disjunction is true. On line 4, both not A and not B are true, again making that, oops, wrong letter, again making that disjunction as a whole true. Okay, so if you look at the pattern of truth values under the main operator for these two sentences, it's FT, T, T. So these are examples of equivalent sentences, and the explanation you would give is like this one here. You would say that these two sentences are equivalent because on every truth assignment to their atomic propositions, the two sentences agree in truth value. Here's another case. Now we have a negated disjunction. I'll solve this in the same way. I'll start by just doing the parenthesis. I've got true, 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 false. And that's just because this is a disjunction. And it's only on the last line that we have two false disjuncts. And then take the negation of those values under this main operator here. And we get F, 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 T. All right. Over here, our main operator is a conjunction. Conjunctions are false when both conjuncts are false. They're also false when there's at least one false conjunct. So they're only true when both conjuncts are true. Now, where is that going to be? Well, that's going to be on the fourth line, right? When A is false, that makes not A true. And when B is false, that makes not B true. So TT in a conjunction gives us a true conjunction. On every other line, we'll have at least one false conjunct. So for example, on line 3, where B is true, not B is false. That means we have a false conjunct making the conjunction false. And on the first two lines, not A is going to be false, and that will give us false for both of those lines for the conjunction as a whole. All right, so both these cases then we have F, 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 T, and again we'll have the same explanation for this truth table that says that on every truth assignment to A and B, these two sentences have the same truth value as each other. That means they're equivalent. Now these two equivalences that I've just given are kind of famous ones. They're called De Morgan's rules. De Morgan was a mathematician and logician. And what this tells us is that we can transform a conjunction into a disjunction, provided that we move some negation signs around. So you can kind of think of this as taking this negation sign and distributing it inside the conjunction, right? But notice that when you do that, the and switches to an or. It's the same thing here too, right? You distribute this negation inside, you apply it to both A and B, but when you do that, you have to change the disjunction to a conjunction. That's a handy trick if you do proofs in kind of logic called natural deduction, which is something that you would learn in the next level course, the 2000 level course, currently called Philosophy 200. It will be called Philosophy 2100 in the semester system. All right, so that's tests for equivalence of sentences. I just want to show you this one as well because it's also pretty useful. What we have here is a conditional if r then x, and what we're going to show is that it's equivalent to the disjunction not r or x. And the way that we can show that is that on line 1, x is true, making the disjunction true. On line 2, x is false, and since r is true, not r is false, so we have a false disjunction there. And then on every other line, we've got at least one true disjunct. We've got the x true on line 3, making the disjunction true. And actually, both of the sentences, both of the disjuncts are true on the 4th line, so we get this same pattern. TF, TT, under the main operator for both of these sentences. So these sentences are also equivalent. Now, one of the interesting things you can do with equivalence is this neat thing here. You can prove that you actually only need 2 connectives to do all the work of the 5 connectives we have in SL. So you can show that you need negation and any one of the other connectives, right? And you can replace all the others. The easiest one to do this for is to use negation and disjunction. You can also do it with negation and conjunction, negation and conditional, and even negation and biconditional. The sentences with negation and biconditional get really long and ugly, but so we won't bother to look at that. But in principle, you could do it that way. So here's what I'm talking about. And we just proved here with this truth table that a conditional is equivalent to a disjunction where you negate the antecedent, turn that into a disjunct, and let the consequent be the other disjunct. All right, so if P then Q is equivalent to not P or Q. And we can show that P and Q is equivalent to not P or not Q. That's actually just a version of De Morgan's rules. Let's go back to those. And what we see is that we've got the idea of distributing the negation sign inside a conjunction to give us a disjunction. So we can do that here if we imagine A and B, and we can think of this as a double negated A and B, right? Because not means the same as just having no negation at all. If you have a negation, well, let's say this sentence A and B is true, the first negation makes it false, the second negation makes it true again. So you could actually put a truth table together where what you were testing was this equivalence between those 2 sentences. But that's easy, you can do that on your own. For our purposes, what I want to just show you is that if you start from this sentence A and B, that's really equivalent to not A and B. And then you can take one of those negations and apply it inside the parentheses. Right? So what do? You get rid of the one outside, right? And then you apply it to the first sentence, so you get not A instead of A. You apply it to the second sentence to get not B, and then you change the conjunction to a disjunction. All right, so that's just using this first version of De Morgan's rules and the idea of double negation. So that's how you can prove that, this sentence A and B is equivalent to this one, not A or not B. And that's exactly what I've got down here when we're talking about equivalences. Something weird happened here and this Q got erased. All right, so number 2 here, P and Q is equivalent to not P or not Q. That's just De Morgan's rules. You can also just put those 2 sentences in a truth table and you'll get the same result, that those 2 sentences are equivalent. Now, the sentence P try bar Q, that's called a biconditional because it's really equivalent to two conditionals. What conditionals are they? Well, conditionals that run in the opposite direction. So you can do a truth table. I'm going to leave this as an exercise for you. I really want you to do this. So if you want to just pause the video right now and do this, that would be a good idea. Prove that P try bar Q is equivalent to if P then Q and if Q then P. Okay, so remember there's technically another set of brackets here, something around this one. This is a pretty easy proof. It's just evaluating those two conditionals and then evaluating the main operator, which is the AND. Okay, so once you've done that, come back and then look at 3a and 3b, which are related to 3. You'll notice that what's going on here is that we have a conditional here that's changing into a disjunction. Well, that's just this first thing that we did, right? That first equivalence. That's the same that's happening here. So you can also put this sentence in a truth table and prove they're equivalent. I recommend that you do that too. Pause the video and prove that. Once you've completed that, now we can talk about 3b. You'll notice that what's happening here is that we've taken this conjunction, we've turned it into a disjunction, and essentially what we've done is that De Morgan's rule that we just talked about. We took the conjunction, right, like this here, we put a negation in front of the whole thing, we negated the first conjunct, changed the sign from disjunction to conjunction, then negated the second sentence. Okay, so that's what we did here. We negated the whole thing, negated the first sentence, this one, and then we negated the second sentence here, meanwhile changing and to or. All right, so you can also do a truth table where you show that P try bar Q is equivalent to this. Recommend again that you do that. If you can do this one, if you can do that truth table, you're in good shape for the test. I think that you've learned this stuff well by now. If you struggle with that, take some time, try it out, and then ask me any questions you might have about it. Okay, so great so far. I hope you're getting it. If not, let me know and we'll work on it together. Now, I want to turn to our next topic, which is to consider validity. Okay. All right, so sorry for all the messing around here. All right, so our next topic is validity. And arguments of SL are valid when there is no truth assignment that makes all the premises true and the conclusion false. Now, I want you to think about this in the context of our definition of validity. An argument is valid when if the premises were true it would be impossible for the conclusion to be false. All right, now that's our definition of when a deductive argument is valid. Compare that definition in green with the way we test arguments with truth tables for validity. So an argument is valid when, if the premises were true, it would be impossible for the conclusion to be false. Arguments of SL are valid when there is no truth assignment that makes all the premises true and the conclusion false. So we're still talking about this condition, right? The premise is true and the conclusion false. And when we say this, that there is no truth assignment that makes all the premises true and the conclusion is false, what we mean is that it's impossible for the premises to be true at the same time the conclusion is false. All right, now why does impossible mean the same thing as there is no truth assignment? Well, that's because when we set up a truth table, the guide column tells us all the possible ways that the atomic sentences involved in the argument can be true and false together. And if none of those truth assignments makes the premises true and the conclusion false, then it's not possible for that argument to have a false conclusion when its premises are true. Okay, so this truth table test is a really neat implementation of the definition of validity. It's also a really nice way to understand more what the definition of validity actually means. Let's explore this through some examples. We'll start with this invalid argument. A or B, B, therefore A. And the way we do a truth table test is that we take the argument and write each of its sentences in its own column of a truth table. Okay, now normally our conclusions are going to be more complicated than just a single letter, but it doesn't matter what the conclusion is, it gets its own column. Same thing for each of the premises, they each get their own column. Now we inspect what we've just written down, right? And then we find the atomic sentences that are in that set of 3 sentences, and that's just A and B. All right, so that tells us our guide column. Then we write down the ordinary arrangement of truth values for the guide column, TT, TF, FT, FF. And now we just have to fill in the truth table. Now, what are we looking for when we fill in the truth table? We'll go back to this definition in red here. Arguments of SL are valid when there is no truth assignment that makes all the premises true and the conclusion false. So if an argument is invalid, that means that there is a truth assignment that makes the premises true and the conclusion false. So that's what we're looking for, is one line of this truth table, at least one line of this truth table, that makes the premises true and the conclusion false. Well, I'm going to give you a little bit of a shortcut here because it turns out that the only time that can happen is when the conclusion is false. And that's only going to happen on the last 2 lines of this truth table because that's where the guide column makes a false. Now, where are the other premises going to be true? Well, it's going to be on line 3 because B is true in the guide column on line 3. That makes the second premise true. And since B is true on that line, that means that the second disjunct of the first premise is true, which means the first premise is true. So we have T, T, F, and that means that this argument is not valid. In other words, it's possible for this argument to have a false conclusion when its premises are true. When is it possible? Well, on the truth assignment, A is false, B is true. We have true premises together with a false conclusion. All right, so it's that truth assignment that shows us that it is possible for the argument to have a false conclusion when its premises are true. Therefore, this is an invalid argument. So there's a standard explanation you're going to give for invalid arguments. It's this one. There is a truth assignment that makes the premises true and the conclusion false. Therefore, this argument is invalid. It's a good idea, I think, to say specifically what that truth assignment is, just to show me that you know what you were talking about. But as long as you say that there is a truth assignment that makes the premises true and the conclusion false, then you said everything you need to say. Good, so that's how you prove invalidity. What about proving validity? Here's a valid argument. Okay, now we write each of the sentences across the top of the truth table. We've got A or B in our first column, not A in the second column, B in the third column for the conclusion. We inspect that and we see there's only A and B as atomic sentences, so we create our guide column that way. By the way, you can't shortcut this. You can't leave out this column for the conclusion because then the truth table doesn't work out properly. So I know that there are some classes and some books even that teach this a little bit differently, but I want you to do it exactly this way or you won't get credit. All right. So fill in the truth table. All right, now what we're going to show is that there is no truth assignment that makes the premises true and the conclusion false. That means we have to look at every single line of the truth table. Now, there are ways to make this shorter, and usually the best strategy is to begin looking at the conclusion. Okay, so always start with the conclusion. Why is that important? Well, because typically only about half of the conclusion, half of the rows for the conclusion are going to give you a false conclusion. Why does that matter? Well, because those are the only cases where it could possibly be that you have a false conclusion together with true premises. All right, so now we know that on line 1 we don't have true premises together with a false conclusion because we have a true conclusion. And on line 3 we don't have true premises together with a false conclusion because we have a true conclusion. So then we only have to worry about lines 2 and 4. And on line 2, since A is true, not A is false. Now again, as soon as we know that we don't have all true premises together with a false conclusion on line 2 because the second premise is false on line 2. Turns out the first premise is true. You could write a T there for the A or B because A is true. But you don't have to. This is enough to show that line 2 doesn't have true premises together with a false conclusion. Same thing on line 4. A is false, so the second premise, not A, is going to be true. So what we need to look at is the disjunction. In that case, both A and B are false. That makes the disjunction false. So that means, again, we have at least one false premise whenever the conclusion is false. And that means that this is a valid argument. So the explanation you would give here is this one. There is no truth assignment that makes all the premises true and the conclusion false. So this argument is valid. Okay, so that's the truth table test for validity. We'll do more with that later. A lot of your exercises over the next week or two will be about proving validity. So I encourage you to make sure that you understand each part of this recording, and if you didn't, then repeat it. And of course, go back to the textbook to make sure that you understand the content there. Send me any questions if you have any. Don't forget about the Logic Lab, which is available to help you try to figure out any problems you might be having. So if truth tables just seem like a mystery to you, go ahead and give them a call, and they can set up a Zoom meeting with you, and they'll discuss it in a way that will help you to understand it even more than I already have. Okay? Take care for now.